Lesson 3 of Chapter 3 is on logarithmic functions and, of course, their graphs. So we've been talking about exponential functions, and if you take a look right here, we have an exponential growth function. And we know it's exponential growth because it's going up and to the right, and every exponential growth function has a base value that is greater than 1. If it's exponential decay, it's going to look something like this. And we know it's exponential decay because it's going down and to the right, and the base value would have to be between 0 and 1. Well, this leads us into logarithms, okay? And so our definition of a logarithm, right here, y equals, this is read, the log of x base b. You can see that little subscript with the b in it. There's going to be a number there, right? So that's true if and only if b to the y equals x. So we have two forms that we can essentially change and go back and forth between. We have exponential form and we have log form. Okay, and so we'll practice going back and forth between those two forms to help us understand logarithms. First example, we have the log of 8 base 2. So this equals 2 raised to some exponent has to equal 8. And so that's our understanding of a logarithm. And so obviously here in this case we know that x equals 3. Part B, we have the log of square root of 3 base 3. So that's the same thing as 3 raised to something equaling the square root of 3. Well, from there we know that if we raise a number to the 1/2 power, it equals the square root. So in this case, x would equal just 1/2. Next one we have the log of 1/25 base 5. And so that's the same thing as 5 raised to something equaling 1/25. Well, 5 squared is 25, and so 5 to the negative 2 would be equal to 1/25. So that's how we get a result of negative 2. Part D, we have the log of 1 base 4. So this means 4 raised to some power equals 1. And of course that answer is 0. Here's a little tip for you guys. Anytime you've got a 1 like this inside of a log, no matter what the base is, whether the base is 4 or 5 or 6 or whatever, your answer is always going to be 0. And then part E, we have the log of 7 base 7. So this means that we have 7 raised to some power equaling 7. And so obviously that answer is 1. Another pro tip. Anytime this number that's inside the log is the same as the base of the log right there, your answer is always going to be 1. Let's look at a couple of other examples. Actually, we've done the first two examples, are A and B. Let's look at that example C. Here we have a logarithm that's inside of an exponent. So to change that from exponential back into log form, that would equal the log of 11 base 6 is equal to the log of x base 6. Those are equal to the same thing. Well, now you can see, since we've got a log base 6 on both sides, we can just cancel that off, and so we get a result of just 11. Here's another little pro tip for you. Anytime you've got an exponential that has a base like 6, and you've got a log in the exponent, and the base of that log is the same as the base of the exponential, your answer is just going to be what's inside the log. So from there, we're going to talk about common logs. Now, common log looks like this, and you can see that this log doesn't have a base written. So when there's no base value written, it's assumed to be a 10 right there. And we just call that a common log, okay? So the log of x base 10 is equal to this, 10 to the y equals x. So here's some common log examples. We have the common log of 100. And so to solve that, we would say 10 raised to what power equals 100? And obviously that answer is 2. Part B, another common log. This time it's the common log of the 5th root of 10. So we'd say 10 raised to what power equals, I'm going to rewrite that fifth root of 10 as 10 to the 1/5 power. And now you can clearly see that your result is 1/5 because the bases are both 10. Part C, we have a common log of 1 over 1,000. So 10 raised to what power equals 1 over, did I say 10,000? I meant to say 1,000. I'm going to rewrite that 1 over 1,000 as 10 to the -3 because 10 to the third is 1,000, so 10 to the -3 is 1,000. And now you can clearly see that your result is -3 because we have two bases there on both sides with the same number. And then part D, again, we've got a log in the exponent position, and so this is the same thing as the log of 6, the common log of 6 would be equal to the common log of x. And again, since we have a common log on the left and a common log on the right, we can cancel those, and we can get our result to be 6. So that's what a common log is. Next, we're going to talk about doing common logs on your calculator. So your calculator has just a log button right here. And so this problem is the common log, what was it, 34.5. And before we hit enter, let's think about this. Our answer should be between 1 and 2 because what's 10 to the first? 10. What's 10 to the second? 100. And 34.5 is between 10 and 100. Now, is 34.5 closer to 10 or is it closer to 100? Of course, it's closer to 10, right? So our answer should be closer to 1 than it is to 2. Oh, shoot. Got that one wrong. All right. And so then the next one we have the log of 0.43. Which gives us a negative result. So that's your common log button. It's located on your calculator. Let's go down here to example 5. This says to solve each equation. We didn't have equations before. We were just evaluating logs, but these are equations now. So you can change these equations from log form to exponential to find the result. You can see that part A, you've got an x inside your log, so the base of that log is 10 because there's nothing written there, so it's assumed to be a 10. It's a common log. So we can change this equation to exponential. It'd be 10 to the third equals x, and then obviously 10 to the third is just 1,000, and so our result is 1,000. Part B, again, we have an x inside of a log. This is not a common log. This is a base 2. So to change this to exponential, we have 2 to the 5th equals x. 2 to the 5th, of course, is 32, which is our result. Next, we're going to talk about natural logs. Natural logs look like this. We use the letters ln instead of log. And you notice that there's no base written here. And so with natural logs, the base is the number e. Now, in case you forgot the number e, it's approximately equal to 2.718. It's a famous number in mathematics invented by a famous mathematician, Leonard Euler. And so again, that's a natural log, and that means the same thing as e to the y equals x. So let's look at a few examples that involve natural logs. Again, it's the same thing as a log, it's just got a special base. So part A, we've got the natural log of the square root of e, and so this means the same thing as e raised to something equals the square root of e. Well, certainly the square root of e is the same thing as e to the 1/2, and so that's how our result is in fact 1/2 on this problem. Part B, we'd have e raised to something equals e to the 5th. Obviously, same bases on both sides. Our result here is 5. And then part C, we have a log in the exponent, okay? So we can change that back into log form. This is an exponential form. We can change it back into log form by saying the natural log of 4 is equal to the natural log of x. Keep in mind these are both natural logs, right? Because the base is e. And so now we can cancel the natural logs on both sides, and we get a result of x equals 4. Now you have a natural log button on your calculator as well, so let's discuss that. We have the natural log button located right underneath the common log button. So there's your natural log, and we have 23.5 to get our result, 3.157 approximately. And the natural log of 0.48 would look something like that. Okay, let's talk now about the graphs of log functions. So what we're looking at right here is an exponential growth function. It goes up and to the right. And again, if it's exponential growth, we know that the base value has to be greater than 1. Well, the red graph is its inverse. It's a log graph. It also goes up and to the right. It also is going to have a base value that's greater than 1. Okay, these are inverses of each other. The exponential growth function, the blue function, has a horizontal asymptote right here at y equals 0. And the log graph, oh, I need a different color. Here we go. The log graph has a vertical asymptote right here at x equals 0. So that's what your log graphs look like when it's log growth. We won't always have log growth. Sometimes we'll have log decay. But this says to describe the transformations. So our parent function is either this, the natural log of x, or the common log of x. So for part A, you can see our parent function is going to be the natural log of x. And how is that parent function different than the one that we're looking at? Well, you can see there's a +2 inside the natural log. Anything on the inside affects it horizontally, and so this is going to shift it 2 units to the left. Part B. This one's a little bit tricky. I'm going to rewrite this natural log function. So I'm going to rewrite it as, I'm going to take the negative out. I'm going to write it as x minus 3. I know that's kind of tricky, but here's why I did that. Now you can see both the transformations a little bit easier. So the first transformation is a shift to the right 3. The second transformation is a horizontal reflection, which is about the y-axis. Okay. Part C. This time we've got a 3 on the outside of the common log. Since it's on the outside, it's going to affect it vertically, and multiplying expands it since the value is greater than 1. So it's a vertical expansion by a factor of 3. And then part D, we've got a +1 on the outside. That's also going to affect it vertically. It's just going to take it and shift it up 1 since we're adding 1. So we'll apply these transformations to log functions just like we have with exponential, with quadratic, with polynomials. We've talked about transformations all year. Let's finish up by doing the quick review. We're going to evaluate these expressions. These are properties of exponents that some students forget about, so it's good to review them. 5 to the negative 2 is the same thing as 5 squared on the bottom of a fraction. So this is the same thing as 1 over 25. 10 to the negative 3 is the same thing as 10 to the third on the bottom of a fraction. That's why this is the same thing as 1 over 1,000. Number 3, 4 to the 0. A lot of people think that that's equal to 0, but you have to remember anything to the 0 power is 1. So we would reduce this into 1/5. Number 4, again, anything to the 0 power is 1. So this would result into 1/2. Now, number 5 is a little bit tricky because we're trying to do this without a calculator. So what I'm going to do is I'm going to change 8 into a base 2. 8 is the same thing as 2 to the third. We still have that raised to the 11th power. And we still have the 2 to the 28th on the bottom. Now, properties of exponents say that we take those two numbers on the top, the 3 and the 11, and we multiply them to get 2 to the 33rd. And this is over 2 to the 28th. And now properties of exponents say that we subtract those to get 2 to the 5th, which we know is equal to 32. Same kind of thing on number 6. We're going to change these both into the same base. Now I'm going to change these into base 3. So 9 is the same thing as 3 squared, raised to the 13th. 27 is the same thing as 3 to the 3rd, raised to the 8th. We'll change the numerator into 3 to the 26th. The denominator into 3 to the 24th. Oh gosh, let's write a 3 there, huh? There we go. Looks better. And so now we subtract these exponents to get 3 to the 2nd, and our result is 9. And then these last 4, it says to rewrite as a base raised to a rational number. In case you've forgotten, a rational number is a number that can be written as a fraction. And so the square root of 5 is the same thing as 5 to the 1/2 power. Number 8, we have the 3rd root of 10. Well, that's the same thing as 10 to the 1/3 power. And number 9, we have the square root of e, and it's on the bottom of a fraction. And so since it's on the bottom of a fraction, we'll have to have a negative exponent. And since it's underneath a square root, it's going to be e to the negative 1/2. Number 10 also has that e, the 3rd root of e squared in the bottom of a fraction. So we're going to have this with a negative exponent. And since it's underneath a 3rd root, we have to have a 1/3, but since it's squared, it's got to be 2/3. And of course, it's negative because it's on the bottom. So I just want to leave you with, I wanted to let you know that I'm not a professional electrician. And usually when I tell people that, they're shocked to find out that I'm not a professional electrician. Be awesome today.